Good morning, and thank you for joining us today. Our presentation today is on the optimal TOC analysis tips on a UV Persulfate system. Joy Osborne is presenting. She is our TOC product line manager. We will be taking questions. You could submit those using the question function, and we will address those at the end of the presentation. Okay, I'm going to go ahead and turn it over to you, Joy.
All right, thank you, Shelley. Like Shelley said, I'm talking about how to optimize the fusion. So that's our UV Persulfate system. So you can see there's a picture of our fusion. Okay. The agenda will start the system off right, meaning make sure that your fusion is in order, it's clean, has good blanks, leak tight, all those good things. So we'll go over that. Basic troubleshooting throughout. So if you do have a high blank or high clean, what does that mean and how do you fix that? And then we'll go over method and calibration curve optimization. So making sure you have the best method and best calibration curve for your application. All right, so just a little bit about the fusion. It's actually our 6th generation UV Persulfate analyzer that we've designed and created from Teledyne Tekmar. It's great for pharmaceutical, environmental, and semiconductor applications. I would say most of our customers either use it for pharmaceutical or environmental, meaning drinking water or clean in place, water for injection type application. So it's really good at the low level carbon analysis. So drinking water and cleaner, it's very, very good for that. All right, so let's start our system off right. So we'll just pretend, you just turned on the system, your fusion. You do want, when you turn on the fusion, you do want to allow some time for it to warm up. So the lamp, the UV lamp on the fusion takes about 30 minutes to be fully intense. So to fully oxidize that carbon, it does take about 30 minutes, so keep that in mind. Sometimes I'll be cleaning it while it's warming up, so that's a good thing to do while it's warming up is to run some cleans. So the first thing I usually do is a leak tight. So symptoms of a gas leak are poor sensitivity, so you're not going to get very good low-end results. If you're trying to do parts per billion analysis, things like that, it's going to be very difficult if you have any kind of gas leak, even a very small one. You're going to get high % off RSD, so if you're running something in triplicate and you get anything above 5%, that's disconcerting on the fusion. Also a low M value, meaning with your calibration curve, your Y equals mx+b equation, the M value will be low. And I'll explain that all more in detail further in this presentation. So we're starting the day off. We're going to do a leak check. One of the things I love about the fusion is that you can automatically do this. It only takes a couple minutes at a time. So it's good while things are warming up. You can go to Tools, Maintenance Tasks, Leak Check, and you can leak check either the UV pathway, so it only pressurizes the sample pathway in the UV, or the IC pathway, or you can do both. I usually do both. If you get a failed leak check, so basically during a leak check, it pressurizes the system to 50 psi, and if it loses more than 1 psi in a minute, there's a leak. So if you get below 49, so you can actually narrow it down where the leak is by knowing if it's in the UV side, the IC side, or both. I didn't put all the flow diagrams in this presentation. So what I'd actually recommend you guys to do if you do have a problem with that is we have a great tech support team. You're welcome to call in and they will help you pinpoint exactly where that leak is. Also with each report or each replicate, each one will report to pressure. So you can see these are all around 50 psi, which is good. If you see that drop below 49, you have a leak. So keep that in mind, just something to keep an eye on while you're running. All right, now that I know my system's leak tight, the UV lamp warms up, all that good stuff, I'm going to add some cleans to the schedule. The Fusion also has an automatic cleaning procedure, which is really, really nice. It not only helps clean the system, but it also lets you know if it's not clean. So again, if you want great analytical analysis, you really need to have a good clean system that's low in carbon. All right, so a little bit about how the cleaning procedure works. So basically a volume of DI water is pulled from the reservoir and is cycled back and forth between the IC sparger and the UV reactor 3 times, once for each TC clean rep. Each time the water cycles through, it is analyzed for carbon content, and an ABS result is reported. The process actually purifies the water, so you're actually purifying the water as you cycle it back and forth. So that lamp is doing its job, it's oxidizing that carbon, and the CO2 is going to the detector. So what you should see is your absorbance counts get lower with each TC clean, and I'll show you that in just a minute. The first TC clean results should be less than 15 absorbance counts, and the third TC result should be less than 5. Anything greater than, let's say, 20 should be a concern. So let's talk about that. Oops, sorry, guys. All right, so here is 2 clean results. On the top is an example of a good clean, and on the bottom is an example of a bad clean. And what do I mean by that? So like I talked about, the first TC rep, which is rep 2, should be less than 15 absorbance counts. And by the third rep, or the fourth one in this, it should be less than 3. So this is an example of a good clean system. So if you want to have really good analytical results, you're going to need a good clean system. All right, and on the bottom is an example of a system that's not clean. It's full of carbon, which is not in your sample. It's either from the system or your DI water. We'll talk about that more, but it's not from your sample, so you're going to report false high results, which you do not want. So you can see here, the first TC clean is above 15 absorbance counts, and the third one is above 3. And as you can see, it's really not dropping down. Okay, so let's talk about different kinds of contamination. So you can actually tell from the clean and the pattern of the clean. It kind of it can indicate where the source of the contamination is coming from. So on the top is an example of bad DI water. So DI water that's high in carbon, which happens a lot. It's actually a very common problem. So here we go. We start off with a high TC clean at 25 absorbance counts. And by the third, we're down to 1.57, which is acceptable. So we're starting out with dirty water, and as that's being cycled back and forth through the UV lamp and being oxidized, it's removing the carbon. Okay, so that's a sign of bad DI water. Now, it may not necessarily be your DI water. It could actually be the reservoir in which the DI water is stored in. So the bottle could be dirty. It could also be the tubing going from the DI water to the Fusion could be contaminated. So those are some things to keep in mind. So obviously, if you're getting a pattern like this, replace your water, clean your water bottle, the bottle that's used, storing the water, things like that. If it's still not cleaning up, it's still showing this pattern, then you want to replace the tubing from the DI water container. And if it still shows it, then you're going to want to look at your 7-port valve. All right. And then the second example is an example of a contaminated system. So again, it started off at 32. It only went down to 30. So while that water is being cycled back and forth between the IC sparger in the UV lamp, the carbon counts are not really going down, which signifies that there is carbon in that sample pathway. So a few things you can do to clean that kind of thing up is run additional cleans, but if it's still not going down or going down quickly, you can run, this little trick I do, I'll run 5% phosphoric acid as a sample, so that 5% phosphoric acid will actually kind of scrub out the sample pathway, okay? So you should start to see numbers come down. If you're still having problems, I would look at your glassware. So a lot of these things should be taken off and cleaned on a regular basis. So one great thing about the Fusion is that all the glassware is very easy to see. It's very visible. It's on the front of the instrument, so you can see when it actually sometimes gets dirty, especially with your icy sparger, which is pictured here. You'll see this, there's a white frit, which helps the bubbling, the icy sparging effect. The sparging effect right here will actually turn brown or yellow. Okay, so that's a sign that it's dirty or contaminated. Usually that discoloration could be a sign there's carbon. So you can see it right away. You can take it off and clean it. So be careful when you clean the glassware. You can use like Alconox or, lab grade soap. That's fine, but keep in mind those things have carbon in them. So you're going to want to acid wash it after you clean it with hot soapy water. I use like a 5% nitric acid solution and then rinse it really good with DI water afterwards, just to make sure you remove all the soap. You do not want soap in your system, so it's always a good idea. Another common place besides the icy sparger that can get contaminated is actually the UV reactor. Okay, so the UV reactor, because it heats up, it seems to kind of bake on some carbon contamination. It makes it harder for the cleaning process to remove. So you can actually just unscrew it here, remove the UV reactor's chamber, clean that real good, and you can actually clean the lamp. Just be careful as well. Again, like I said, you can use hot soapy water, but then again, rinse it real well with acid solution and DI water after. I have had that happen before. Okay. Other areas you want to look at if you have contamination in your system is your syringe. Bear in mind your syringe is a consumable, so it can get contaminated, things like that. Also your water trap. It's good to clean that every once in a while. You'll sometimes see little particulates actually collect at the bottom of that water trap. And then your 7-port valve, just because it's moving all those liquids around, it easily can, the pathway inside can easily be contaminated. Okay. Another sign of contamination, I see this sometimes. If you're a halogen scrubber, it's supposed to be, one side's supposed to be shiny like a copper penny and it turns dull. When there's a lot of halogens on it, that's fine. But if you start to see like browning around your Pyrex wool, or it's turning different colors like a green, or things like that, that could be a sign of contamination. Just so, again, it's something you can easily just look at and know. And again, the halogen scrubber is consumable. We recommend replacing that. Even if you have clean samples, you're running every 1 to 2 years, it's a good thing to replace that. Okay, all right, so let's say you have some dirty samples and you can tell they're carrying over from one rep to the other, one sample to the other. There are some things you can do within the Fusion software and inside the method to help clean it out for you. So to help do that job for you of cleaning. So you're going to want to open up your method, whatever it is. We do have some great already programmed methods inside the Fusion that give you a good starting point. So some things you'll want to change in your method is to turn on the UV reactor pre-rinse. So what that does is it gives that UV reactor chamber and that lamp an extra rinse. And then you can tell it what volume, if you turn this on, what volume you want it to. It's a good idea to use a volume that you're rinsing with that's greater than your sample volume, just so that liquid goes up higher in that fusion chamber and cleans down those walls, those glass walls from any carbon. Okay? And then you can even tell it to do it more than once if you like. If you have really dirty samples or you're showing carryover, just bear in mind the more UV reactor rinses you do, the longer your analysis time. So there is some trade-off there. Okay, and this is all under the general tab. And then just so you know, there's also an advanced tab with each method optimization. You will get this window that pops up that kind of says you should, understand these parameters before changing them. Just be aware of that, but you can change them. It's safe. It's just you could change your method dramatically if you start really messing around with these numbers. But a few things that you definitely can not worry about is the needle rinse volume. So again, to help with carryover, you can rinse the sample needle. So that's the needle that goes down into the sample vial and punctures the VOA vial or whatever kind of vial you're using. And then you can actually even rinse the IC sparger. Okay, so you can also increase that. Okay, so those are some ways you can help clean up your system just through the method. All right, let's talk about restrictions. So as it's running, sometimes just to verify if I see anything like higher speeds or something I don't like, I will sit there and actually watch it run for a little bit. And I will make sure I don't see any signs of restrictions. So here is my 25 ml syringe. A good indicator, and it's a very easy way to discover you have a restriction, is if you get any air bubbles, like significant air bubbles on the top of your syringe when it comes to pull liquid. Okay, so obviously if your syringe is trying to pull liquid and there's a restriction in the line, it's going to make it very difficult for it, and it's going to end up pulling air. Okay, so you'll see quite a bit of bubbles on the top. All right, so things that can cause a restriction is a pinched line. So you can see here, this tubing has been pinched. So, the flow through it, the liquid flow through it is not optimal. So you're going to have some problems there. You can also get particulates sometimes from your sample. I've even seen a little bit of the rubber of the septum from the sample vial get in the sample pathway. The stuff can happen. So that can cause a restriction or blockage, of course. And then the other thing I want to warn you guys about is sodium persulfate. So when sodium persulfate dries out, it becomes a white powder. And that white powder can become a restriction, especially in that 7-port valve. So I recommend, if you're not using it, that's fine if you don't use diffusion for a few days, but it's good to run a clean or blank or something through the system while it's not running, so it doesn't dry out and that white powder from the sodium persulfate doesn't accumulate. So just a little, as you're walking by, hit clean or something if you haven't been using it. Okay, and then if you're trying to find the restriction, we have some troubleshooting things in the software that will help you pinpoint where it's located. So here's your 7-port valve. Here's it in the software. It's actually under Diagnostics Pumper. So what you would do if you see you're starting to accumulate bubbles or have a sign of restriction, you can go to each spot on that 7-port valve and pull a volume of liquid and see if it's in that pathway. The only thing I do want to warn you about is you don't want to just pull waste through your system. That's a good way to contaminate your system. So what I do is take that line out of the waste container and put it in a beaker of DI water and I usually do that one last, the waste. I check all the other ones before I would go to that, because you don't really, it's not, you wouldn't really see a restriction in the waste line that would affect your analytical results. So, you know, I go to B first and then C, you know, go to B, pull an aliquot of liquid, make sure no major bubbles are forming. If they are, I know it's between the samples, so that would be the sample vial on top of the tray and the sample needle, the line going down to the 7-port valve. Somewhere in there is a restriction. Common place for a restriction is actually sometimes the ferrules at the end that screw into the 7-port valve can become crimped. So it's good to unscrew them and look at them and make sure there's no clog there, that kind of stuff. So you would repeat that and see for each area on the 7-port valve if it's causing a restriction. Okay. All right. Now that we've cleaned the system, we've talked about contamination and restrictions. Let's run a blank. All right. I do recommend running a blank, you know, fairly often, maybe daily. Okay. And the reason I do that is I like to see the results from a blank. So a blank actually runs a clean first. So same idea. You can run a blank as a clean too, if you'd like. You should see less than 15 absorbance counts for the first TC clean and less than 3 absorbance counts for the third TC clean. So this looks like a good clean system. The water looks fine. The system looks fine. So then you go to your blank. So your blank will indicate if you have high carbon in your reagents or high carbon in your acid. Okay, so the reagent blank should be less than 15 absorbance counts, and the acid blank should be less than 3 absorbance counts. And you're wondering, why is there such a discrepancy between the reagent and the acid? Well, first of all, the reagent blank actually uses 3 mils of sodium persulfate, which is injected and then analyzed, just like a sample would be. And the acid's only 1 mil, okay? But even with that said, the reagent has a little bit more wiggle room because sodium persulfate is known to always kind of have a little bit of carbon. I would say between your water and your sodium persulfate, you're always going to have some carbon backgrounds. I know, like my system, my water system usually contributes about 50 parts per billion of water, or sorry, 50 parts per billion of carbon into my water, and then my reagent can be another 10 parts per billion. I know that may change from system to system and site to site slightly, but personally I don't like to see water that runs higher than 150 parts per billion and reagents that run a reagent that runs more than 40 or 50 parts per billion of carbon. It shouldn't be contributing that much. That's not good. So again, you're not going to get accurate, good results if you have that much carbon coming from other sources. Okay. So if your blanks are high, you can always make new sodium persulfate reagents and new 21% phosphoric acid solution. Maybe they got contaminated. Again, also make sure the bottles in which they are stored are clean and carbon-free. You can also replace the tubing if it's still not working. And then again, if that still doesn't work, then the 7-port valve. So if those are coming out high, those are the things you want to look at. Okay, let's talk about baseline. So as it's running, you should also just make sure the baseline looks okay. So the Fusion graphs the baseline as a blue line. Now it should be fairly steady, of course. This is an example of a bad baseline, something's going on. So, and it also reports it in your reports. So you can see it's going from 2.77 to 6.83 to 4.90. It really shouldn't be fluctuating more than, you know, one max 2 PS, or not 2 PSI, ABS counts. And you can see it's really affecting these results. So you're getting high RSCs. Like I said, anything above 5% is probably is disconcerting. So this is coming out too high. Obviously, if the baseline's all over the place, it's not integrating very well. So you're getting results all over the place as well. So then that's contributing to your high RSC. So what do you do if you have a bad baseline? Well, that's it could be, it's usually two things that can cause that. It's your gas supply and your detector. I'm hoping everyone out there is using lab grade nitrogen for their fusion. Some people think they can use air or oxygen. I just want to warn you guys, it does work. It still will oxidize. Your samples will still oxidize if you're using air or oxygen for your fusion. But the chemical oxidation reaction, that sodium persulfate and UV lamp, that's oxidizing the carbon in your sample, is also oxidizing your carrier gas. So you're actually turning that oxygen, that O2 to O3, so you're getting ozone. And the reason that's bad is because ozone's harmful for to your respiratory system, so you're venting ozone out. We do have an ozone scrubber. If you do want to go that route to just save money, you definitely need an ozone scrubber, and you need to stay on top of that. So that's just one thing to consider. So with the gas supply, if you have an inconsistent baseline, you know, check your tank, check your generator. It's a time for it to be, you know, it's a time for preventative maintenance, things like that. Sometimes you get towards the end of a tank, you can kind of pull up some nasty stuff that's at the bottom of the tank that can contain carbon, and you're going to get a baseline like that. So just things to check. And then your detector. So sometimes your detector, let's say the contamination has gotten all the way through your system to your detector. It can also show up as an inconsistent baseline. The nice thing about the detector is it's very easy to access. So you just take this panel, the right panel off of the fusion, just a couple screws holding it on, and everything's pretty much right there that you need to get to. So here's your detector down here, your perm dryer, your mass flow controller, your valve, pressure regulator, you know, things like that. Most of the stuff is right there. It's very easy to get to. It's not crowded or anything. So if you think you have a dirty detector, so what you're going to do is you're going to turn off the instrument, of course. There is electricity going to it, okay? And then you're going to unhook the detector. So you're going to unhook here, here, and here. And then you're going to spray 50% isopropyl and water solution inside the detector. Okay, and then I put my fingers over these two holes and shake it gently. So what that's going to do is that solution's going to try to clean that ruby lens inside the NDIR detector, okay? And then you're going to dump out the contents, so try to get as much liquid out of the detector as possible. And then you're going to only hook up the gas end line and your electrical, okay? And then you're going to turn your instrument back on, and then I just go to diagnostics and set the gas flow to like 300 mils a minute, and I just let it flow. You know, this is going to be still open for 2 hours, so it's just going to dry it out. And then after you do that, you can put your other line on and run it again. So you can clean up the detector if that's an issue. If you need help again with any of this, please feel free to call tech support. All right. Let's talk about, now that we've talked about common things that can go wrong with your system, or, you know, things like that you should be checking on a regular basis to make sure your system, your fusion's running correctly. Let's talk about optimizing the method. All right. So there's something, this is another thing I really enjoy with the Fusion, is that it almost does the work for you. So, and by that I mean, so let's start with optimizing for your sample range. So it actually calculates, if you see here, the optimal sample range for the method you've created. So if you do, so of course, if you decrease the sample volume and increase the dilution, that range is going to open up and get bigger. Let me see if I can actually show you guys in the software. I think it shows it better. So this is an actual live software of the Fusion. So you can see right here is my optimal sample range. Okay, so as I increase the dilution factor, that range increased. So increased from 20 to 50. Also, you can decrease sample volume, same idea. So with that said, the narrower the calibration, or the sample range, I should say, the better results you will get. So the more accurate and precise your results will be. So you want your sample range to be as tight as possible. Now, let's say you have a method, the typical, sorry, I typed in 90, I'm saying that's too many mils for 25 mil syringe. Obviously it is. All right, so the typical pharmaceutical method, which is 9 mils, no dilution, it only goes to 6.7. Okay, you're running samples. Occasionally you get a sample that's above 6.7. Don't worry too much about that. The Fusion has this great feature, which is called IntelliDilution. So it'll actually take the sample that's above the range, the sample range, and dilute it back down to the calibration range. So bear that in mind. If you do get occasional sample outside your sample range, it's not the end of the world. So yeah, you want it, that sample range, as tight as possible for the most accurate and precise results you can get. All right, so let's go back to here. All right, talked about that. And then optimizing it for your sample matrix. So something else you need to consider is what kind of samples you're running on the system. There's a few things you should consider. Again, mostly for Fusion, it's going to be pretty clean samples. You're going to have pretty clean water samples. But if you don't, some things you need to consider is if your samples have salt. So the Fusion can only handle about 0.5% of salt. And seawater, you know, water from the ocean is about 3.5%. So that's way too much for the Fusion. Typically, you know, we strongly recommend combustion systems, not UV persulfate systems like the Fusion for this kind of application, but maybe once in a while you get a sample with salt in it. It's okay. There's some things you can do to accommodate for that. So the problem with salt is it actually disrupts the UV persulfate reaction. So it's going to prevent it from oxidizing, and then you're going to get false low results in your samples. So again, something you need to consider, it needs to definitely be under 0.5%. So you want to increase the dilution factor. So you up that. All right. And then the other thing is, since it tends to disrupt that reaction, you're going to want to increase your reagent volume. So again, sodium persulfate and the UV light are what oxidize that sample. So if you're going to make it difficult for the system, let's help it out by increasing the reagent volume and increasing the pre-sparge time. So that's the time the sample just sits in the UV reactor chamber. So UV light and sodium persulfate are still there. So as it sits there, again, that just gives it more time for the oxidation to occur, and then you can get a good result. Okay. Another thing to consider is your samples have high inorganic carbon. So things like sodium bicarbonate, can make it a little more tricky. So if you don't remove all the inorganic carbon from your sample, you're going to have false high results. So you're going to get a carbon reading and an inorganic carbon reading in that carbon. So what you need to do is increase the acid volume, okay, and then increase the icy sparge time. Now I get the question is, how do you know when I get all the icy out of my sample? So you can develop a couple different methods. You're going to have to do a little bit of method development work. You know, so you're going to want to develop 3 or 4 methods that have varying amounts of acid and icy sparge time that are increasing. And when that number stops going down, you know you've hit the point where you've completely removed all the inorganic carbon. So you might have to do a little bit of method development work, but you know you can do that in one schedule. It's not a big deal. Another thing I want to talk about is a lot of laboratories out there preserve their samples with 1% acid, which is fine. You can definitely do that. You know, you may want to do that if you can't run them right away, because if you don't preserve them, obviously they're going to grow bacteria, and bacteria contains carbon, and then you're going to get higher results than you want. But if there's already 1% acid in the sample from you preserving it, you actually don't need as much acid in the method. You can actually lower that down to almost to nothing if you want, because there's already acid in the sample, so by the time it sparges, it's still going to remove the inorganic carbon for you. Okay, so if you're doing, you know, TC minus IC analysis, I wouldn't really recommend preserving or things like that, because you might accidentally remove some of the IC before you actually analyze it. Okay. All right, let's talk about optimizing the calibration curve. This is an example of a calibration curve from the Fusion. So it reports out like that. The things I'll be talking about is the equation y equals mx plus b, the coefficient of correlation, or the R-squared value, things like that. So that's what I'm talking about right now. Okay. So calibration requirements. So these are things I also keep an eye on to make sure the Fusion's running correctly and I'm getting optimal results, is these factors. So the R-squared I always expect on the Fusion 3 nines. Of course, it's up to you and your SOP of your laboratory. Some only require 995, that's fine. Some require 4 nines. I look for at least 3 nines personally. So that's just a guideline, it's not a rule. The n value, so y equals mx plus b, n, or the slope of the line, should be how many mils are in your method times the factor of 6.5. So if you're running a wastewater method, which is a 4 mil method, it should be times 6.5, which is 26. So it should at least be 26 your slope. For 6 mil method, 39. 9 mil method, it should be 58.5. So again, so you have to calculate it. If you have a dilution factor in there too, you have to, you know, divide it by that dilution factor. So if it's 1 to 10, it's going to be 2.6, the dilution. So those are things you want to watch. Okay, and we'll talk about if you have a low n value, what that signs of later. And the b value, so in y equals mx plus b, so that's where it crosses the y-axis. Okay, so for a 4 mil method, it should be less than 7. For a 6 mil method, it should be less than 8. For a 9 mil method, it should be less than 9. Percent RSDs, less than 5. Usually I shoot internally for less than 2. The pressure, like I said, a normal running system should be 49.2 to 50.8. So if it drops down below 49.2, we've already talked about that. That's a sign of a leak. The baseline should be 0 to 5. So if it's above that, you know, that's a sign your gas is contaminated, your detector is dirty, or you need to do a detector offset or something like that. And your blank. So if you run a blank, these are what? So that blank, not meaning by the reagent blank or the acid blank, but by running a DI water as a sample. That's what I mean here. So 4 mil method should be less than 20, 30, 45, okay? So some of the things you can get out of the calibration is if you have a low M value, that's actually could be a very good indicator that you have a leak. So you're losing some of your carbon throughout your whole calibration curve, so that's going to make your slope not as steep, of course, so you're going to get a lower M value. And then the high B value is a sign of contamination. So if you got a high B value, you got a dirty system, you need to clean, which we talked about earlier, okay? All right, and then tips for check standards. Just real quickly, the check standards are supposed to be in the middle of the calibration range. Every once in a while I get, sometimes people do it outside the calibration range, and then it's really hard to get accurate, good results, obviously, if it's outside the calibration range. So then we'll get really high results, high RSPs, that kind of stuff. It should, if you want good check standards, they should be close to the calibration points, meaning if you run a 1 ppm calibration point, then you can run a 1 check standard. If you kind of skip over that whole range and then you run a check standard there, it may not be as accurate. So keep that in mind. And another thing to keep in mind is to run them the same way as your samples. So if you're preserving your samples with 1% acid, you should preserve your check standards with 1% acid, things like that. So that verifies that your calibration curve is making up for any kind of sample preparation or matrix effects that you're doing with your samples. All right, so here's just an example. Somebody who ran a 0.2 to 10 ppm and then ran a check standard at 0, and then it came up really, really high. So again, it's outside the calibration range, so it's really hard to get good, accurate results outside of the range. All right, and then we've actually come to our conclusion of, do we have any questions? I'm gonna give you guys a minute to come up with any questions.